What existed before the Big Bang? Space, the final frontier, a canvas of infinite darkness punctuated by light so ancient that the civilizations who first looked up and wondered at it have long since turned to dust. We have named the stars. We have traced the spiral arms of distant galaxies. We have listened to the gravitational echoes of colliding black holes. We have mapped the oldest light in existence, the faint, cool afterglow of creation itself. And yet, for all of this, for all the rockets and radio telescopes and quantum detectors and supercomputers and centuries of accumulated brilliance, one question remains so fundamental, so stubbornly resistant to resolution, that even posing it correctly is a challenge. A question that reaches not into the depths of space, but into the depths of time. Past every galaxy, past every star, past the first atom and the first particle of light, past the edge of everything we know. What was there before the beginning? Not before the beginning of humanity, not before the beginning of Earth, or of the solar system, or of the Milky Way, before the beginning of everything, before the Big Bang, before space, before time, before the laws of physics as we understand them had any arena in which to operate. This is perhaps the oldest question our species has ever asked. Every culture that has left a record of its thinking has some version of it. Every tradition, every mythology, every philosophical school has grappled with it in some form, and for most of human history, it was considered beyond the reach of science. A question for theologians and philosophers, not for experimenters and mathematicians. But in the last century, something remarkable has happened. Physics has grown bold enough and mathematically sophisticated enough to begin making serious, testable proposals about what might have preceded the Big Bang. Not myths, not metaphors. Actual mathematical frameworks grounded in our best confirmed theories of nature, reaching backward through time to the moment of origin and daring to ask what came before. Today, we journey to the very beginning and beyond it. The problem with the beginning. Before we can ask what came before the Big Bang, we need to understand precisely what the Big Bang was. And more importantly, we need to understand what makes the question so extraordinarily difficult. The Big Bang was not an explosion. This is one of the most persistent misconceptions in all of popular science, and it matters enormously for understanding why the question of what came before it is so thorny. An explosion is an event that happens at a particular location in a pre-existing space. A bomb detonates. A pressure wave expands outward. The space in which the explosion occurs was there before the explosion happened, and it is still there afterward. The Big Bang was not like this. The Big Bang was an event in which space itself came into existence. There was no pre-existing void waiting to be filled. There was no stage already set. Space, time, matter, and energy all emerged together from a state of extraordinary density and temperature, expanding and cooling in a process that has continued for 13.8 billion years and is still ongoing today. This distinction matters because it transforms the question of what came before the Big Bang into something genuinely strange. If time itself emerged from the Big Bang, then the phrase "before the Big Bang" may be as meaningless as the phrase "north of the North Pole." Not meaningless in a dismissive sense. Meaningless in the precise sense that the concept of "before" requires the existence of time. And if time did not exist before the Big Bang, then there was no before. This is the answer that, for many years, served as the standard scientific response to the question. The universe began at the Big Bang. Time began at the Big Bang. There was no before, because there was no time in which a before could have occurred. Case closed. But the case, it turns out, is far from closed. And the reason it is not closed comes down to a single, stubborn mathematical fact. The Big Bang, as described by general relativity, is a singularity, a point at which the density of matter and the curvature of space-time become, in the language of the equations, infinite. And in physics, infinity is almost never an answer. Infinity is a sign that a theory has been pushed beyond its range of validity, that something is missing, that a more complete description is needed. General relativity, our best theory of gravity and of large-scale space-time structure, breaks down at the singularity. Its equations cannot meaningfully describe the state of the universe at the very moment of the Big Bang, let alone before it. And this breakdown is itself a clue. It tells us that the Big Bang was not, in the description offered by general relativity, truly a beginning. It was simply the moment at which general relativity runs out of descriptive power, a more complete theory, one that reconciles general relativity with quantum mechanics, the framework that governs physics at the smallest scales, might describe what happens at and before the singularity in a way that general relativity cannot. And it might reveal that the Big Bang, far from being an absolute beginning, was merely a transition, a dramatic, universe-reshaping transition, but a transition nonetheless. From what to what is what the great theoretical frameworks of modern physics are now beginning to tell us. The echoes we can hear. Before we explore what theory proposes, it is worth understanding what observation has already told us about the earliest moments we can access. The oldest light we can detect is the cosmic microwave background radiation, the CMB. It is the faint thermal glow left over from a moment approximately 380,000 years after the Big Bang, when the universe had cooled sufficiently for neutral atoms to form and for photons to travel freely for the first time. Before that moment, the universe was an opaque plasma, and no electromagnetic signal from earlier times can reach us through it. The CMB is our deepest electromagnetic window into cosmic history, and it is extraordinary. Mapping it with the precision achieved by the WMAP and Planck satellites has yielded measurements of the universe's age, geometry, composition, and the spectrum of primordial fluctuations that seeded all subsequent structure. It is, in the words of more than one cosmologist, a baby picture of the universe, a snapshot of the cosmos at 380,000 years old. But those primordial fluctuations, those tiny variations in temperature of roughly 1 part in 100,000, carry information about what happened even earlier. They are the imprint of quantum fluctuations that existed in the very early universe, stretched to cosmic scales by the period of rapid expansion known as inflation. And their statistical properties, measured with great precision by satellite missions, constrain what conditions were like at times far earlier than 380,000 years, far earlier, in fact, than the first second. The abundance of light elements, hydrogen, helium, deuterium, and lithium, forged in the first 3 minutes after the Big Bang through a process called Big Bang nucleosynthesis, provides another window. The precise ratios of these elements, measurable in ancient stars and pristine gas clouds, agree with extraordinary precision with the predictions of the standard cosmological model when the temperature of the early universe is extrapolated back to the energies of nuclear reactions. This tells us that our understanding of particle physics was already correct when the universe was a few minutes old. Neutrinos offer a glimpse even further back. These nearly massless, almost non-interacting particles decoupled from the rest of matter roughly 1 second after the Big Bang. A background of relic neutrinos, analogous to the microwave background but originating from this earlier moment, is predicted to fill the universe today. Its effects are indirectly confirmed through the precision cosmological measurements of the CMB and the large-scale structure of the universe. But directly detecting these relic neutrinos, cooled and redshifted by 13.8 billion years of cosmic expansion to extraordinarily low energies, remains beyond the reach of any current technology. And gravitational waves represent the deepest possible window. Unlike electromagnetic radiation, gravitational waves pass through the plasma of the early universe without scattering. If inflation produced a spectrum of primordial gravitational waves, and the leading inflationary models predict it did, those waves are propagating through space today, their fingerprint encoded in the polarization pattern of the cosmic microwave background. Detecting them is one of the primary goals of the next generation of CMB experiments and of future space-based gravitational wave observatories. But even gravitational waves cannot tell us about the Planck epoch, the first 10 to the power of negative 43 seconds, the moment at which the energy density of the universe was so extreme that quantum gravitational effects dominated everything. Before that frontier, all our observational tools fall silent. And beyond that frontier, our theories are, for now, blind. This is where observation hands the baton to theory, and where theory, in the last several decades, has produced some of its most audacious and remarkable proposals: the oscillating universe. Breathing in and breathing out. The oldest scientific framework for addressing what came before the Big Bang is, in some sense, also the most intuitive. It asks a deceptively simple question. What if the Big Bang was not a beginning, but a bounce? What if the universe, rather than emerging from nothing, had contracted from a previous state, reached a point of minimum size, and then rebounded into the expansion we observe today? This is the essence of the oscillating universe model. The universe breathes. It expands for billions of years, slows, stops, and then contracts. As it contracts, galaxies fall together, stars collide, matter is compressed toward a point of extreme density. But instead of reaching a true singularity from which no future emerges, quantum effects intervene, halting the collapse and driving a new expansion. A new Big Bang. A new universe beginning its own billions of years of expansion, structure formation, and perhaps the emergence of new forms of complexity and life. In this model, our Big Bang was preceded by a contraction, and before that contraction, a previous expansion, and before that another contraction, and before that another expansion. The series extends backward, potentially without limit, a cosmic rhythm of creation and destruction that has no first beat and may have no last. The appeal of this picture is enormous. It resolves the singularity, or at least proposes to, by replacing the absolute beginning with a dynamic transition. It eliminates the philosophically uncomfortable notion of something emerging from nothing. And it provides an infinite backstory for a universe that might otherwise seem uncomfortably orphaned in time. But the oscillating universe model faces serious challenges. The most fundamental comes from the second law of thermodynamics. In every physical process, entropy, the measure of disorder in a system, either stays the same or increases. It never spontaneously decreases. And if the universe oscillates, each cycle must presumably begin with a higher entropy than the last, because the contraction and re-expansion cannot perfectly reset the thermodynamic state. This means that as we trace the oscillating cycles backward in time, each previous cycle must have had lower entropy. The cycles become shorter and less complex. And eventually, if we go back far enough, we arrive at a cycle so short and so simple that it barely constitutes a universe at all. The oscillating model, pressed by thermodynamics, does not eliminate the problem of a beginning. It simply moves it further back. Modern versions of the bounce cosmology have attempted to address these problems with more sophisticated physics. Loop quantum cosmology, in particular, offers a rigorous framework for the bounce. In loop quantum gravity, space itself is not continuous, but is composed of discrete, indivisible units. A quantum foam of space at scales far smaller than any we can currently probe. At the extreme densities of a collapsing universe, these quantum properties of space generate a repulsive effect that overwhelms classical gravity, halting the collapse and driving a new expansion. In loop quantum cosmology, the Big Bang becomes the Big Bounce. The singularity, which general relativity predicts and cannot move beyond, is replaced by a moment of maximum density that is finite and physically well-defined. The universe before the bounce was contracting. The universe after the bounce, our universe, is expanding. And the mathematical tools of loop quantum gravity can, at least in principle, trace the evolution through the bounce, connecting the contracting phase to the expanding one in a way that is free of singularities. The predictions of loop quantum cosmology are, in principle, testable. The details of how quantum gravity modifies the spectrum of primordial fluctuations at the bounce may leave subtle imprints on the cosmic microwave background that differ from the predictions of standard inflation. Finding those imprints, or failing to find them at the level predicted, would constrain the model. The measurements required are extraordinarily demanding, but they are not impossible. What would have existed before the Big Bang in this framework? A universe. A different universe, perhaps very similar in its physics to our own, but contracting rather than expanding, growing denser and hotter rather than cooler and more diffuse. A universe that reached its minimum, bounced, and became us. And before that, another expansion, another contraction, another bounce. The chain extends backward as far as the mathematics can be trusted, which may be very far indeed. The no-boundary proposal, a universe without a beginning. In 1983, physicists Stephen Hawking and James Hartley proposed something genuinely radical. Not that the universe had a different beginning than the Big Bang, not that it had an earlier phase before the Big Bang, but that it had no beginning at all. Their proposal, known as the no-boundary condition or the Hartle-Hawking state, arises from the attempt to apply quantum mechanics to the entire universe as a single physical system. In ordinary quantum mechanics, we describe the state of a system, a particle, an atom, a field, with a mathematical object called a wave function, which encodes the probabilities of all possible outcomes of measurements on that system. Hawking and Hartle asked what the wave function of the entire universe might look like. To construct this wave function, they used a mathematical technique called the path integral, borrowed from quantum field theory. In the path integral approach, the probability of going from one state to another is computed by summing over all possible histories connecting those states, each weighted by a factor that depends on the action, the integrated energy, of that history. Hawking and Hartley applied this to the universe itself, summing over all possible four-dimensional geometries of space-time. And they imposed a crucial boundary condition. They required that the sum include only compact geometries, geometries that are closed, like the surface of a sphere, with no edge and no boundary. The result is a universe that, in a very precise mathematical sense, has no beginning. Just as the surface of the Earth has no boundary, you can travel in any direction without falling off an edge. The universe described by the no-boundary proposal has no temporal edge. The concept of time in the very early universe becomes indistinguishable from a spatial dimension. There is no moment of creation because there is no moment before which the universe did not exist. Time itself smoothly emerges from a regime in which the very distinction between time and space is blurred. This is not an easy concept to visualize. Our intuition for time, its directionality, its asymmetry, its inexorable flow from past to future, is so deeply embedded in our cognition that imagining a regime in which time dissolves into space feels almost physically impossible. But mathematics does not need our intuition's permission, and the Hartley-Hawking proposal is mathematically precise. The question, what came before the Big Bang, in the no-boundary framework receives a very specific answer. Nothing. Not in the sense that there was empty space and empty time before the Big Bang, but in the sense that the question itself does not apply. Asking what came before the Big Bang in a no-boundary universe is like asking what lies south of the South Pole. The directions runs out. The question has no referent. But this does not mean the no-boundary proposal is merely a clever way of dismissing the question. It makes predictions. It tells us that the universe would emerge in a specific quantum state, described by the wave function that Hartley and Hawking compute. From this wave function, the probable properties of the early universe, its size, its smoothness, its fluctuations, can in principle be derived, and those properties can be compared with what we observe. The no-boundary proposal has faced significant theoretical debates since its introduction. Some calculations suggest that the most probable universe emerging from the Hartley-Hawking state would be empty, rather than like the rich, structured universe we observe. Others argue that the predictions depend sensitively on how the path integral is defined and regulated, and that different but equally reasonable choices of mathematical procedure yield different predictions. These debates are live and unresolved. The no-boundary proposal is not a finished theory. It is an ambitious program, a direction of inquiry, a demonstration that the question of the universe's origin can be addressed within the framework of quantum physics without requiring a boundary condition imposed from outside. Whether the specific proposal of Hartley and Hawking is ultimately correct, it has permanently changed the landscape of the question. What came before the Big Bang? In the no-boundary framework, the very grammar of the question needs to be revised. The past does not extend through the Big Bang to something before it. It curves smoothly, geometrically, into a state in which there is no earlier time to point to. The universe is self-contained, complete, its own cause and its own origin, eternal inflation, and the bubble that became everything. Among the theoretical proposals for the origin of the universe, few are as sweeping in their implications as the framework of eternal inflation, and few have as much genuine scientific credibility in the sense of being a direct consequence of ideas developed to explain observational data rather than purely speculative constructs. Inflation, the idea that the very early universe underwent a period of extraordinarily rapid, exponential expansion, was proposed in 1980 by physicist Alan Guth, motivated by a specific set of observational puzzles. The uniformity of the cosmic microwave background across regions of the sky that should, without inflation, have had no causal connection. The near-perfect flatness of the universe. The absence of certain exotic particles predicted by high-energy physics theories that would have been produced abundantly in the early universe if it had not inflated. Inflation solved all of these problems elegantly by positing that the observable universe originated from a tiny, causally connected patch that was then stretched to enormous size in a fraction of a second. The uniformity, the flatness, the missing relics, all followed naturally from even a brief period of inflationary expansion. But inflation, developed to solve specific observational puzzles, turned out to have implications that went far beyond those puzzles. In most models of inflation, the inflationary expansion does not stop everywhere at once. It stops locally, in a region that then becomes a more slowly expanding space like ours, but continues in surrounding regions, which keep inflating. And within those still inflating regions, quantum fluctuations cause inflation to end in some places, producing new, slowly expanding pockets. And around those pockets, inflation continues, producing yet more pockets. This process, called eternal inflation, produces an unbounded number of pocket universes. Each pocket is, from the perspective of its inhabitants, an entire universe, bounded by its own cosmological horizons, governed by its own version of the laws of physics, with its own history of structure formation. Our universe, in this picture, is one such pocket, one bubble among an infinitely, or at least vastly, large number of others. The inflating background in which these pockets form is not a place in the ordinary sense. It is a region of space-time driven by the enormous energy of the inflaton field, the hypothetical field whose potential energy drives inflationary expansion. In that background, space expands so rapidly that it can never run out. New space is created faster than pockets can form and end inflation. The process continues forever into the future, and may have been ongoing forever into the past. What existed before the Big Bang, in the framework of eternal inflation? The inflationary background, an eternal, exponentially expanding sea of space and energy, from which our pocket universe condensed when inflation ended locally in our region. The Big Bang, in this picture, was not a beginning. It was a phase transition, a moment at which the potential energy driving inflation in our region was converted into the hot, dense plasma of particles and radiation that we call the Big Bang. Before that phase transition, our region of space was different. It was inflating. It was cold in a certain sense. The energy was stored as potential energy of a field, not as the thermal energy of particles. It was vastly simpler on some measures than the complex structured universe that followed. But it was not nothing. It was a physical state. A state governed by physical laws. A state that had preceded our Big Bang by however long that particular region had been inflating before the transition occurred. The implications of eternal inflation reach further. If each pocket universe can have different values of the fundamental physical constants, different strengths of the fundamental forces, different masses for elementary particles, a different value of the cosmological constant, then the question of why our universe has the specific properties it does, receives a new kind of answer. Not that those properties were selected by a creator or required by some deep principle of uniqueness, but that they were selected by the anthropic principle, the observation that we can only find ourselves in a pocket universe whose properties permit our existence. This is either the deepest insight or the most dangerous dodge in modern physics, depending on whom you ask. The debate about the anthropic principle and the multiverse of eternal inflation is one of the liveliest and most contentious in contemporary theoretical physics. But it is a debate conducted with mathematical precision and observational constraint, not philosophical hand-waving. And at its center sits the question of what came before. In eternal inflation, the answer is not a different universe in sequence, as in the bounce models, but a different kind of universe in parallel, an inflationary background that never had a beginning and never ends, from which islands of slower expansion, like bubbles in an endlessly boiling sea, continuously form and evolve, the ekpyrotic universe. When worlds collide. String theory is the most ambitious theoretical framework in modern physics. It proposes that the fundamental constituents of nature are not point-like particles, but tiny, one-dimensional vibrating filaments of energy, strings, whose different modes of vibration produce the different particles we observe. And it requires, for mathematical consistency, that space-time has more dimensions than the four, 3 of space and 1 of time, that we experience. The extra dimensions of string theory are typically assumed to be compactified, curled up at scales too small to be directly detected. But a different possibility was explored in a remarkable proposal developed in the early 2000s. What if some extra dimensions are not compactified? What if they extend macroscopically, but in directions perpendicular to the 3 spatial dimensions we inhabit? In this picture, our universe is not the whole of space. It is a 3-dimensional surface called a brane, short for membrane, embedded in a higher dimensional space. Other branes may exist, parallel to ours, separated by a small distance in the extra dimension. And these branes, though they occupy the same higher dimensional space, are effectively invisible to each other because the particles of ordinary matter are confined to their respective branes and cannot cross the extra-dimensional gap. The exception is gravity. In most brane world models, gravity is the one force that can propagate through the extra dimensions, which is why it is so much weaker than the other fundamental forces. Its strength is diluted by spreading into the additional space. From this framework emerged the ekpyrotic model, whose name derives from the ancient Greek concept of a world periodically consumed and reborn in fire. In the ekpyrotic scenario, our Big Bang was caused by the collision of 2 branes. Our brane and a neighboring brane, separated by a tiny gap in the extra dimension, were drawn together by an attractive force between them. They approached each other, accelerating as they came, and when they collided, the kinetic energy of the collision was converted into the hot, dense plasma of particles and radiation that we call the Big Bang. In this model, what existed before the Big Bang is extraordinarily concrete. Another brane, another universe perhaps on that brane, though the collision would have destroyed or fundamentally transformed whatever structure had existed there. A vast, cold, nearly empty higher dimensional space, and the slow gravitational approach of 2 cosmic membranes over an immense span of time. The ekpyrotic scenario offers a natural explanation for the smoothness and flatness of the universe, without invoking inflation, at least in its original form. As the branes approach each other, the contracting extra dimension can smooth out inhomogeneities and generate the nearly scale-invariant spectrum of primordial fluctuations that we observe in the CMB. The same mechanism that makes our universe uniform also makes it flat. But the ekpyrotic model has a sequel. Inspired by the brane collision as a potentially cyclical event, Paul Steinhardt and Neil Turok proposed the cyclic ekpyrotic model. In this version, the branes do not simply collide once and then separate forever. After the collision, they separate, expand, cool, develop structure, and then, drawn together again by the interbrain force, begin a slow approach, collide again, and repeat the cycle. Each collision is a new Big Bang. Each expansion is a new cosmic age. The process repeats indefinitely. The cyclic ekpyrotic model resolves several conceptual difficulties of standard cosmology. It requires no special initial conditions. It does not need an inflaton field or a mechanism to end inflation. Each cycle naturally sets up the conditions for the next one, and it provides a literal answer to the question of what came before our Big Bang, a previous cycle, a previous expansion that stretched the branes apart, cooled them, allowed structure to form, and then drew them back together for the next collision. The cyclic model makes specific observational predictions that distinguish it from inflationary cosmology. In particular, it predicts an essentially zero amplitude of primordial gravitational waves, far below the detectability of any planned experiment. Inflation, in most of its variants, predicts a detectable amplitude. If next-generation CMB polarization experiments detect primordial gravitational waves, the cyclic model faces a serious challenge. If they find nothing, the cyclic model survives and inflation is constrained. The contest between these models may be decided within decades, or it may remain unresolved, the theoretical landscape more complicated than any single experiment can illuminate. But the debate itself is one of the most scientifically productive in modern cosmology, driving the development of more sensitive instruments and more precise theoretical predictions, the string landscape, and the prehistory of physical law. There is another dimension to the before the Big Bang question that deserves its own careful attention. Not just what physical state preceded our universe, but whether the laws of physics themselves had an origin. Whether the constants of nature, the speed of light, the charge of the electron, the strength of gravity, were determined at the moment of our Big Bang or fixed earlier, or perhaps could have been different entirely. In the standard cosmological model, the laws of physics are simply given. They are the framework within which the universe evolves, but the model has nothing to say about why those laws have the form they do, or why the constants have the specific numerical values they take. These are free parameters, numbers that must be measured rather than derived, plugged into the equations rather than predicted by them. String theory offers a different perspective. In this mathematical framework, the fundamental laws of physics in 4 dimensions emerge from the geometry of the extra dimensions that string theory requires for consistency. Different ways of curling up those extra dimensions into small, intricate shapes produce different effective laws of physics in the 4 large dimensions we experience. Different particle masses, different force strengths, a different cosmological constant. The number of distinct geometrical configurations consistent with string theory is estimated to be approximately 10 to the power of 500. This is a number so vast that it genuinely defies comprehension. 10 to the power of 500 different possible universes, each with its own version of physics, its own particle content, its own fundamental constants. This enormous collection of possibilities is called the string theory landscape. In the context of eternal inflation, the landscape takes on a profound significance. If inflation produces pocket universes in astronomically large numbers, and if each pocket can settle into a different region of the string theory landscape, when inflation ends locally, then the multiverse of eternal inflation is not a collection of copies of our universe. It is a collection of radically different universes, each governed by different physics, each exploring a different corner of what is physically possible. What this implies for the before the Big Bang question is subtle but important. If the laws of physics in our universe were determined by the specific geometric configuration that our bubble settled into when inflation ended, then those laws were not fixed before our Big Bang in the way we might naturally assume. They crystallized at the Big Bang, much like water freezing into a particular crystal structure. Before the Big Bang, in the inflating parent space, the physics was the high-energy physics of the inflationary epoch. Vast, hot, governed by laws that differ from our own in ways we can only begin to characterize. This means that whatever preceded our Big Bang did not obey our laws. The speed of light in the inflating background, if the concept meaningfully applies there, may have been different. The masses of any particles that existed were different. The cosmological constant was enormous, the enormous energy density of the inflaton field, rather than the extraordinarily tiny value we observe today. Before our Big Bang, there was a universe with different rules. The debate around the string landscape is one of the most contentious in modern theoretical physics. Critics argue that with 10 to the power of 500 possibilities, the framework predicts almost nothing, because almost any observation can be accommodated somewhere in the landscape. A theory that can explain everything explains nothing. Defenders respond that the correct approach is to develop statistical and anthropic tools for extracting genuine predictions, arguing that some regions of the landscape are far more common than others, and that observer selection effects constrain which regions we should expect to find ourselves in. The debate is unresolved, and the tools needed to make the landscape scientifically precise are still being developed. But the question it raises about the Big Bang is real, not just what physical state preceded our universe, but whether the rules governing that state are the same as the rules governing ours, and if not, what the rules were, and how the transition between rule sets occurred at the moment of our cosmic birth. Part 7. Quantum Tunneling from Nothing. All of the frameworks discussed so far posit something before the Big Bang: a contracting universe, an inflating background, colliding brains, a previous cosmic cycle, something physical existing in time from which our universe emerged. But there is a different class of proposals that takes the question of the beginning more seriously. Proposals that attempt to describe how a universe might emerge not from a prior physical state, but from something more radical, from quantum nothingness. In quantum mechanics, the vacuum is never truly empty. Virtual particles flicker in and out of existence, borrowing energy from the vacuum for infinitesimal moments and then returning it. This quantum frothing of the vacuum is not merely a theoretical convenience. It has measurable consequences. The Casimir effect, the tiny attractive force between two closely spaced metal plates in a vacuum, arising from the modification of quantum fluctuations between them, has been measured in laboratory experiments and agrees with quantum mechanical predictions. Now, extend this idea. If the quantum vacuum can fluctuate, producing transient particles and fields, could it also fluctuate in a more dramatic way? Could it produce not just particles, but an entire universe? This is the proposal associated most prominently with the physicist Alexander Vilenkin, developed in a seminal 1982 paper. Vilenkin proposed that the universe arose through a process of quantum tunneling from a state of literally nothing, not empty space with quantum fields, but a state with no space, no time, no matter, no energy, no dimensions of any kind, into a state of existence. Quantum tunneling is a well-established phenomenon in ordinary quantum mechanics. A particle, encountering a potential energy barrier that it classically could not surmount, can nonetheless appear on the other side of the barrier, with a probability determined by the height and width of the barrier and the mass and energy of the particle. Alpha decay, the process by which an atomic nucleus emits a helium nucleus, is the most familiar example, and it is explained quantitatively and accurately by quantum tunneling. Radioactive half-lives, verified in countless experiments, depend on tunneling probabilities that quantum mechanics computes correctly. Vilenkin proposed that an analogous process could apply to the universe itself. Mapping the problem of cosmic origin onto the mathematics of quantum tunneling, he computed a wave function for a universe tunneling into existence from a state of nothing. The result suggested that universes could spontaneously come into existence through quantum processes without requiring any prior physical state. The phrase "from nothing" requires careful handling here. Vilenkin's nothing is a precisely defined mathematical state, a state of zero radius, zero volume, no dimensions. It is not the ordinary physicist's vacuum, which is a quantum field theory state full of fluctuations and energy. It is something more radical than that. But it is also not a completely undefined or arbitrary starting point. It is a specific mathematical boundary condition, and from it, quantum mechanics, applied with appropriate assumptions, generates a probability distribution over possible universes. The most probable universes emerging from this tunneling process are the smallest ones consistent with subsequent inflation. A tiny, closed universe, perhaps a few times the Planck length in radius, appears from the quantum nothing and then undergoes exponential inflationary expansion. In a fraction of a second, this microscopic seed becomes the enormous, structured universe we observe today. What came before this? In Vilenkin's framework, the question has no answer, not because we are ignorant, but because the very concept of before dissolves at the tunneling event. Time itself is a property of the universe that emerged through the tunneling. There was no time before the tunneling occurred, so there was no before. The universe is, in a very precise sense, a self-contained quantum event that created its own temporal framework as part of its emergence. This proposal shares with the Hartley-Hawking no-boundary condition a certain philosophical elegance. Both attempt to describe the universe as self-originating, owing nothing to any prior physical state. But they approach this goal with different mathematical tools and different assumptions, and they make somewhat different predictions for the observable properties of the universe. The debate between them, and the broader question of which approach to quantum cosmology is correct, is one of the deepest and most technically demanding discussions in modern theoretical physics. It sits at the intersection of quantum mechanics, general relativity, and cosmology, and it cannot be resolved without a complete theory of quantum gravity that has not yet been fully developed. And yet, the fact that such a discussion can be conducted at all, that the question of the universe's origin can be framed in the language of wave functions and path integrals and tunneling probabilities, represents one of the most extraordinary achievements of human thought. We are asking, with mathematical precision, how existence itself began, the seeds of structure and the arrow of time. Whatever came before the Big Bang, something about it determined the state of the universe immediately afterward. And that initial state had a very specific and deeply puzzling property. It was extraordinarily ordered. This statement requires unpacking. The early universe was in many ways obviously disordered. It was a near uniform, near featureless plasma of particles and radiation, enormously hot and dense, with tiny fluctuations of 1 part in 100,000. That sounds like chaos, but thermodynamically it was not. Thermodynamic order is not the same as structural complexity. A low-entropy state is one with few accessible configurations, one in which the system is highly constrained. And the early universe, despite its apparent simplicity, was thermodynamically special in exactly this sense. Gravity had not yet had time to do its work. Matter was distributed almost uniformly. Black holes had not formed. The entropy stored in gravitational degrees of freedom was negligible. Gravity changes everything over time. As the universe evolves, gravity causes matter to clump. Stars form and burn. Black holes accumulate mass. The gravitational entropy of the universe increases enormously. The universe today, with its billions of galaxies, each containing billions of stars, each surrounded by vast amounts of interstellar medium and dark matter, and punctuated by black holes of various sizes, has far higher gravitational entropy than the early universe did. This is why time has a direction. The second law of thermodynamics, entropy increases, is simply the statement that the universe evolves from low entropy states to high entropy ones. We remember the past and not the future because the past was more ordered. Causes precede effects because order propagates from the initial low entropy state. And this means that whatever came before the Big Bang must account for the extraordinarily low entropy of the Big Bang itself. If our universe emerged from a previous contracting universe, why was the entropy at the bounce so low? If it tunneled from nothing, why did it tunnel into a low entropy rather than a high entropy state? If it formed as a bubble in an inflating background, what determined that the initial conditions within the bubble were thermodynamically special? This is the problem that physicist Roger Penrose has called the most fundamental unsolved problem in physics. And he has proposed a radical solution under the name conformal cyclic cosmology. In Penrose's framework, the far future of our universe and the Big Bang of a successor universe are the same thing, viewed through a mathematical transformation called a conformal rescaling. The idea rests on a remarkable mathematical property of the equations of physics. At extreme low temperatures and densities, in the very far future of a universe in which all black holes have evaporated through Hawking radiation and all massive particles have decayed, physics becomes conformally invariant. That is, it becomes insensitive to the absolute scale of sizes. An enormous, cold, nearly empty universe and a tiny, hot, dense universe are, under conformal rescaling, mathematically equivalent. Penrose proposes that the far future of one cosmic aeon, one complete expansion cycle, is conformally equivalent to the Big Bang of the next. The end of one universe is, mathematically, the beginning of another. The incredibly low entropy of the Big Bang is not a puzzle, because the high entropy of the previous aeon's far future maps, through the conformal rescaling, to a low entropy starting state for the next aeon. What came before the Big Bang in conformal cyclic cosmology? A previous aeon, a previous universe, complete with its own stars and galaxies and black holes, which evolved through its own history, reached its own far future, and smoothly transitioned through the conformal equivalence of its final state with a new initial singularity into our Big Bang. And before that, another aeon. And before that, another. Penrose's model makes specific observational predictions, particularly the presence of circular patterns in the cosmic microwave background, concentric rings of slightly different temperature, arising from the collision of supermassive black holes in the previous aeon, whose gravitational radiation imprinted rings on the CMB. Whether such patterns have been detected is a matter of active scientific debate, with some researchers claiming evidence for them, and others arguing that the claimed signals are statistical artifacts. The debate is ongoing. What all these models share, the bounce, the no boundary, eternal inflation, the ekpyrotic scenario, quantum tunneling, conformal cycles, is the recognition that the Big Bang was almost certainly not an absolute beginning. Physics, when applied carefully and consistently to the most extreme conditions, consistently produces pictures in which our Big Bang was a transition, not a creation from nothing. The question is what kind of transition, and from what kind of prior state? Time before. Time. There's a conceptual trap that makes this entire discussion harder than it needs to be, and it is worth addressing directly. When we ask what existed before the Big Bang, we are using the word before in its ordinary temporal sense. We mean earlier in time. We mean what occupied the moments preceding the moment of the Big Bang. And this question, posed in this way, presupposes that time existed before the Big Bang, that there were moments preceding it in which something could exist. General relativity tells us that time is not a fixed background. It is a dynamical structure, part of the fabric of space-time, which is shaped by matter and energy, and which can have different geometrical properties in different regimes. The time we experience, linear, directional, uniformly flowing, is not a universal given. It is a property of the particular space-time we inhabit. In the very early universe, at energies approaching the Planck scale, the notion of a smooth, continuous time may break down. Loop quantum gravity suggests that time, like space, is fundamentally discrete at the Planck scale, not a continuous flow but a sequence of distinct quantum steps. Below the Planck time, the concept of temporal ordering may not apply at all, and in the no-boundary and quantum tunneling proposals, time emerges as part of the universe's creation. There is no external temporal framework within which the universe's origin occurs. Time is internal to the universe, not prior to it. The question, what came before, cannot be answered by pointing to an earlier time, because there was no earlier time. This is genuinely hard to absorb. Every other question about origins we have ever encountered has assumed the existence of time. The origin of life occurred at a particular moment in Earth's history. The origin of the solar system can be dated. Even the origin of the universe, the Big Bang, has an age, 13.8 billion years. We are accustomed to origins taking place in time, with a before and an after. the possibility that time itself had an origin, that there was a regime, a state, a mathematical structure from which time emerged as a derived or approximate concept, requires a radical revision of our conceptual framework. And it is a revision that our intuitions resist strenuously, because those intuitions were built by evolution for navigating a universe in which time already exists and flows in a definite direction. But physics has required conceptual revolutions before. The Copernican revolution displaced Earth from the center of the cosmos. Special relativity revealed that simultaneity is relative, that there is no universal now shared by all observers. General relativity revealed that space and time are not fixed stages on which physics plays out, but dynamical participants in the play. Quantum mechanics revealed that physical systems do not have definite properties until they are measured, and that the act of measurement is not passive, but transformative. Each of these revolutions demanded that we revise intuitions that felt completely secure, and each of them turned out to be correct, verified by experimental tests of extraordinary precision. The revolution that may be required to answer the question of what came before the Big Bang, a revolution in our understanding of the nature of time itself, may be the most profound yet. And it is underway in the equations and arguments of theoretical physicists working at the boundary of what is currently known. What existed before the Big Bang? The most careful answer that modern physics can give is this: the question, in its ordinary form, may not be well posed. Time, in the regime before, or at the Big Bang, may not have been a continuous, linear dimension like the time we experience. What we can say is that our universe emerged from an extreme state, whether a bouncing quantum space-time, a colliding brane, a fluctuation in an inflating background, or a tunneling event in some mathematical sense, and that the properties of our universe bear the imprints of whatever that prior state was. Reading those imprints with ever more precise instruments and ever more sophisticated theory is our best path to an answer. What the question teaches us. There is something worth pausing on before we reach the end of this journey, something that is easy to miss when we are deep in the details of wave functions and bouncing universes and colliding branes. The question of what came before the Big Bang is not a question we are close to answering, despite the extraordinary sophistication of the frameworks we have explored: loop quantum cosmology, the no-boundary proposal, eternal inflation, ekpyrosis, conformal cycles. None of them is confirmed. None of them has produced a prediction that has been tested and verified in a way that decisively distinguishes it from the alternatives. We are, in the language of the field, still in the era of model building and theoretical exploration. And yet the question has already taught us enormous amounts. The effort to understand what came before the Big Bang has driven the development of loop quantum gravity, one of the most active and promising approaches to the reconciliation of quantum mechanics and general relativity. It has sharpened our understanding of inflation and its alternatives. It has produced the no-boundary proposal, which changed the way physicists think about the relationship between quantum mechanics and cosmology. It has motivated the search for primordial gravitational waves in the CMB, one of the most ambitious observational programs in modern astronomy. The question has also pushed physicists to confront the nature of time at a deeper level than any other line of inquiry. The recognition that time may be emergent, that it may arise from a more fundamental quantum substrate rather than being a given background, has implications that extend far beyond cosmology. It touches the foundations of quantum mechanics, the interpretation of the wave function, the origin of the arrow of time, and the nature of causality itself. And the question has a quality that few scientific questions possess. It cannot be avoided by looking away. Every other question in physics, however deep, sits within a framework that assumes the existence of a universe. Questions about the nature of dark matter, the mechanism of high-temperature superconductivity, the reconciliation of quantum mechanics and gravity, all of these are questions about the contents or the laws of a universe that is already there. The question of what came before the Big Bang questions the universe itself, its origin, its necessity, whether it had to exist at all, or whether it is one of many possibilities, or whether the concept of its necessity is even well defined. It is the point at which physics and philosophy most intimately embrace, where the demand for empirical verification meets the limits of what can, even in principle, be empirically accessed. We are, as a species, remarkably young. Anatomically, modern humans have existed for perhaps 300,000 years. Recorded history spans roughly 5,000. The scientific method in any recognizable form has been practiced for perhaps 400 years. And in that brief span, we have managed to reconstruct the history of a universe 13.8 billion years old, to peer within a fraction of a second of its origin, to develop mathematical tools capable of addressing what might have preceded it. This is, by any measure, extraordinary, and it suggests that the remaining distance between where we are and where we need to be, between today's speculative proposals and a confirmed, empirically grounded account of cosmic origins, may be traversable. Not quickly, not easily, not without the development of theoretical frameworks and observational technologies that do not yet exist, but traversable. Each generation of physicists has inherited an open question that seemed, to previous generations, permanently beyond reach. And each generation has found, often through developments that surprised everyone, new paths through the obstacles. The history of science is not a history of permanent barriers. It is a history of barriers that one by one have yielded the answer that changes everything. We began with a question: what existed before the Big Bang? And we have traveled through some of the most extraordinary landscapes in all of theoretical physics in pursuit of it, bouncing universes and inflating backgrounds, colliding membranes and quantum tunneling, cycles without end and beginnings without precedents, proposals in which time dissolves and others in which it stretches infinitely backward. We have not found the answer, not the final, definitive, empirically confirmed answer that would settle the question for all time. That answer does not yet exist. Perhaps it is decades away. Perhaps it is a century away. Perhaps it requires a revolution in theoretical physics as profound as the ones that gave us quantum mechanics and general relativity, a revolution whose shape we cannot currently predict. But we have found something else, something that may, in its way, be just as valuable. We have found that the question is answerable in principle, that it is not permanently beyond the reach of science, that the tools of physics, quantum mechanics, general relativity, thermodynamics, information theory, can be brought to bear on it with genuine force, generating testable predictions and meaningful constraints. The question is hard. It is perhaps the hardest question ever posed in a scientific framework, but it is not hopeless. And we have found that every serious attempt to answer it has enlarged our understanding of nature in ways that go far beyond the question itself. The effort to understand what came before the Big Bang has taught us about the quantum nature of space-time, the thermodynamic arrow of time, the possibility of other universes, the nature of inflation and its alternatives, and the deepest structure of the relationship between quantum mechanics and gravity. The universe, it turns out, is not merely the contents of space and time. It is the arena within which all existence plays out, and potentially one arena among many. One episode in a story that may have no beginning and no end, one bubble in an eternal sea, one cycle in a rhythm older than time itself. Or it is something even stranger, a self-contained quantum event that created its own temporal framework, a universe that tunneled into existence from mathematical nothing, bringing time and space and all the laws of physics with it. A universe that is, in the deepest sense, its own explanation. We do not yet know which of these pictures, if any, is correct, but the asking itself has value. The reaching matters. Every generation that poses the deepest questions and pursues them with honesty and rigor pushes the frontier another step outward. Every measurement made, every theoretical framework constructed, every prediction tested, whether confirmed or refuted, adds to the map. The map is still mostly blank at the edges. The territory it represents extends into regions that no human eye has seen and no human instrument has probed, but the blank spaces are not permanent features. They are temporary. They are the next destination. Because here is the truth that every chapter of this story has quietly been building toward. The universe began. In some sense, we do not yet fully understand. And whatever came before it, whatever physical or mathematical reality preceded the first moment of our cosmic existence, was real. It shaped the universe we live in. It determined the properties of the first instant, the initial conditions from which everything followed. It is part of our story, even if we cannot yet read it. And the fact that we are here, on this small planet, orbiting this ordinary star, in this unremarkable corner of an extraordinary cosmos, asking these questions with the full force of mathematics and physics and human curiosity, that fact is itself remarkable. The universe has produced, from the expansion of a hot, dense plasma, creatures who want to know where the plasma came from. That impulse, that refusal to accept the horizon as a final boundary, is what has carried us this far. It is what will carry us further. The question remains open. The journey continues. And whatever lies at the beginning of everything is waiting, patiently, to be found. The privilege of the unanswered. Question. In the long history of scientific inquiry, there is a pattern worth noticing. The questions that proved most transformative were rarely the ones that admitted easy answers. They were the ones that resisted, the ones that forced the development of entirely new mathematical languages, entirely new experimental approaches, entirely new conceptual frameworks before they could even be properly posed. The question of what came before the Big Bang is, by any measure, the most resistant question science has ever taken seriously. It sits at the intersection of every unsolved problem in fundamental physics. It requires, for a complete answer, a theory of quantum gravity that does not yet exist. It may require an understanding of time itself that goes beyond anything our current frameworks can offer. It reaches into a regime so extreme that no experiment we can currently conceive would probe it directly. And yet we ask it. We ask it because the alternative, accepting a permanent boundary on knowledge, a forever unanswerable question at the foundation of everything, is something the scientific temperament finds genuinely intolerable, not from arrogance, not from the naive belief that all questions are answerable, but from the hard-won historical knowledge that questions which seemed permanently beyond reach have repeatedly yielded to the right combination of ingenuity and persistence. Consider how recently the Big Bang itself was unknown. In 1900, the dominant scientific view held that the universe was eternal and essentially static. The idea that it had a beginning was not taken seriously by most physicists. By 1965, the discovery of the cosmic microwave background had transformed the Big Bang from a speculative hypothesis into the established foundation of cosmology. In 65 years, humanity had gone from not knowing that the universe began to measuring the temperature of the light left over from its beginning. Or consider the question of the universe's age. For most of human history, an answer seemed permanently out of reach. The universe was old, that much was clear. But how old? What instrument could possibly date the cosmos? And yet the answer came, through the chain of reasoning connecting the expansion rate of the universe to its geometry, to the composition of its oldest stars, to the temperature and polarization of its oldest light. We know the age of the universe to an accuracy of better than 1%. A question that was literally unanswerable for all of prior human history has been answered in the span of a single lifetime. The question of what came before the Big Bang will be answered, perhaps not in a single lifetime, perhaps not through a single decisive observation, but through the gradual accumulation of constraints from gravitational wave measurements, CMB, polarization observations, particle physics experiments probing the high-energy frontier, and theoretical advances in quantum gravity that we cannot yet predict. Perhaps the answer will be something none of the current frameworks have imagined, but the answer will come. And when it does, it will not merely fill in a gap in our knowledge. It will transform the way we understand the nature of time, the origin of physical law, the relationship between quantum mechanics and geometry, and the place of our universe in the larger context, whatever that context turns out to be, of all that exists. We live in a rare and extraordinary moment. We are the first generation with instruments sensitive enough to probe the cosmic microwave background at the precision required to test theories of cosmic origin. The first with gravitational wave detectors capable of registering events across the observable universe. The first with particle accelerators reaching energies where the physics of the early universe becomes accessible in terrestrial experiments. The first with the theoretical tools, loop quantum gravity, string theory, quantum cosmology, conformal cyclic cosmology, to make mathematically precise proposals about what came before the beginning. We are not at the end of this story. We are somewhere in the middle, and we cannot yet see how far the middle extends. The question is open. The journey is ongoing. The territory ahead is vast and largely unmapped, but we are moving, and every step forward, every measurement made, every theory refined, every prediction tested, brings us closer to the moment when someone, somewhere, in some future era equipped with tools we cannot yet imagine, will read the answer, will trace the history of the universe back through the Big Bang and through whatever preceded it, and will understand, finally, where all of this came from. What existed before the Big Bang? We do not know yet, but we are asking, and in science, the asking has always been the beginning of knowing.